Okay, so today we're going to talk about the concept of complexification, which has more general applications than, we specifically have in mind using this for Lie algebras, specifically, even more specifically, I hope is that if you've been following along with these videos, which there's some gaps in, you'll be able to jump ahead to section 7.2 and 7.3 of Hall's book on Lie groups and Lie algebras, and not have to worry about, what does it mean that a Lie algebra came from a compact group or whatever. We're gonna this video will allow you to circumvent having to read all that background, I hope. But there are more general applications, like complexification is really important, say, for example, in differential geometry, which we're not going to worry about, but if you wanted to talk about the tangent space of a complex manifold, that's really an important concept there. So this story sort of begins with the observation that, suppose we had some vector space V, and this is a complex vector space. Well, it turns out if you have a complex vector space, and let's suppose that the dimension of this vector space was n, then we sort of naturally get a real vector space. How do we get that real vector space? Well, we basically look at all the every vector, and well, we have, by the fact that this is a complex vector space, we know that we have a real multiplication, right? Simply by the natural inclusion of the real numbers in the complex numbers, right? So we do already have scalar multiplication by the real numbers, and it acts given the complex scalar multiplication that we have. And it turns out, if we have a basis for the complex vector space, then you can show that simply taking each of these vectors and then that vector, that should be v1 times I dot 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 all the way up to vn I, or that's the scalar product up to here, this will form a basis for the underlying real vector space. So if you have an n-dimensional vector space, then the underlying sort of real vector space will have dimension 2n, generally speaking. Okay, so that's one way in which we go from complex vector spaces down to real vector spaces. And so now we might suspect that, well, is there a reverse process? Can we take a real vector space and create a complex vector space? Yes, the answer turns out. And so, the fancy way to do it, if you happen to know about tensor products, which we're going to talk about a way you can do it without tensor products, losing but it's nicer. It's nicer this way. So if you know about tensor products, if V is a real vector space, then you can tensor with the complex numbers and you can get a complex vector space. And so this is, maybe the more typical way to define the complexification of a vector space. But we can also give another explicit construction of this. So we could also define the complexification of a real vector space to be all pairs where u and v are vectors in V. And so we give this the obvious vector space structure that you would on, say, the in terms of the additivity that you would with just taking the direct sum of V with itself, except we want the scalar, we sort of want to think of u plus iv, or this pair uv as being like u plus iv, right? And so we already have a real scalar multiplication, and you can see that in order to define the scalar multiplication of an arbitrary complex number, it would be enough to simply tell you, because A and B are real, right? So from making the other vector space axioms satisfied, it's enough to tell you what I should do. So you basically just look at, well, how would the scalar multiplication of I on this thing act? Well, you would end up with I, U minus V, right? And so if we go and express that in terms of our pair, we demand that the scalar multiplication of I on this pair sends it to the pair minus VU, right? So now we end up getting a complex vector space, right? So if we have V complexification, so if we started out with a real vector space, then we would get a complex vector space, which is twice the real dimension of V, right? So in fact, this isn't some sort of bijection, right? That is, if we imagine we started with a complex vector space, right? So this has, let's say, the complex dimension of this was n. Well, then if you went and you looked at the underlying sort of real vector space, so maybe I'll call it V sub r to say that it comes from V. So this will have real dimension 2n. And then if you were to go and complexify that thing and look at its complex dimension, you should have 4n, dimension 4n, I believe. Oh, that's not true. Actually, it'll still be 2n. It'll still be 2n. Better double check me on that. But in any case, the point is this is not a bijective process. Now, I'm going to pause to say some fancy words for those of you who happen to know. But you can, maybe skip ahead. We're going to talk about some of these things in an unfancy way, but let me maybe just mention, before I say that, here's an exercise through either the tensor product definition or this formal one I've just given you. Notice that the complexification of the real numbers is the complex numbers, and the complexification of the complex numbers is C2. So that's a good exercise to work out these things. Okay, so some fancier stuff is that I should mention that these processes also give you a way, if you have, say, a complex, you have a linear transformation of complex vector spaces. And if you did this sort of forgetting down to the real vector spaces, this induces, so I'll leave it to you to think about how exactly you define it, but that should induce a linear transformation on the real vector spaces. And same thing with complexification. If you started with a real linear transformation, complexification gives you a complex linear transformation. And sort of the fancy way to package together all of those nice things is that this process is functorial. So we have a functor from real vector spaces. We have a pair of functors from real vector spaces to complex vector spaces. And in particular, one thing you should always suspect is that if you have two categories, C and D, and you have a functor that is forgetful, right? So for instance, if D is our category of complex vector spaces, the process of taking a complex vector space and just sort of forgetting about the complex scalar multiplication, right? So it's going from a complex vector space to a real vector space is a sort of forgetting operation. In general, you should expect that forgetful functors have some sort of adjoint, which is often some sort of free functor. So I'll leave you to meditate on that if you happen to know about those things. And maybe I'll just briefly mention as well that everything I've mentioned here has a much more general manifestation in the concept of rings. So if you have a homomorphism of rings, you get various homomorphisms, various functors between the module categories induced by this homomorphism. So you basically get this triple adjunction. And if you look up on my channel, I have a video called Adjunction Junction, where I talk about these things and how they're related to, say, induction and restriction of representations of groups. Okay, that's the end of the sort of more abstract part. Let's talk about the consequences for Lie algebras. That's what we're ultimately interested in. So yeah, one of the benefits of being able to change perspectives is that you can use facts about complex algebras or complex vector spaces to study real ones and vice versa. So what we're going to do then is, since our Lie algebra is some vector space together with a this bilinear bracket, well, it's a vector space. So naturally, you should think about, well, do all the vector space operations extend to Lie algebra operations? And now we see that, well, now we have this new operation of complexification, or forgetting the complex structure of a vector space. We should ask if we can extend that to the level of Lie algebras. And indeed, so what do we need to do? So if I have a real Lie algebra and I consider its complexification using any of the definitions above, we might think about how we would want to extend. We can also, to give you one sort of less rigorous definition, you can always just think of it as some sort of formal span of formal linear combinations, where X and Y belong to the underlying real Lie algebra, right? And so under this, and I'll leave it to you to make it more precise using either definition we used above, how should we define the Lie bracket on the complexification? Well, I claim that it should be, and again, if you use basically all you need to do, much like how we figured out, oh, what should the scalar multiplication be in terms of the complex vector space, just remember that we do have expressions where if A and B belong to our underlying real Lie bracket, then we know that this thing is defined, and we know that we want this thing to be bilinear. So I claim if you simply expand that out, think about multiplication by I and bilinearity, then we can define this in terms of the original Lie bracket to be the following expression. And ooh, I'm going off screen a little bit there. So yeah. Okay, so I will again leave you to meditate on that, and to, well, all you really need to do is prove that this is a Lie bracket following the definitions, the definition, or using the fact that we already know that on G we have a Lie bracket, except now, of course, this is supposed to be bilinear with respect to complex multiplication, where written in this form, complex multiplication acts, scalar multiplication acts in the sort of obvious way. So generally speaking, then you can prove that if we have a real Lie algebra, but realized as, say, a subset, but subalgebra of n by n complex matrices, then the complexification can be described as, well, I maybe should have said this part first before I defined the Lie bracket as such, but the complexification can be viewed as this. So what are some interesting examples? Well, I suppose, so for those of you who do have access to it, well, it is on my my Google pages, which maybe my Google site, which I'll link below. In my master's thesis, I worked out, well, you can find these lots of places, but for example, I worked with the Lie algebra UPQ. And even though this is defined in terms of complex matrices, you actually find that in general it has odd real dimension, and therefore it actually can't possibly be a complex vector space. So it sits inside MP plus QC, but it is a real Lie algebra, and then you can compute the complexification of it. So more generally, you can view GLN-R, again, just via the natural inclusion of the real numbers into the complex numbers. You can view this as sitting inside GLN-C, and or rather, perhaps I should say you should view it as sitting in MNC, and then, as you might expect, GLN-R, its complexification is isomorphic to GLN-C as a Lie algebra. So that is actually, you can find the proof of this in 317 of Hall. So one of the things we want to talk about is the notion of compact algebras. And again, the point of this video is basically to allow you to circumvent having to pass through, compactness of Lie groups. So here's just a list of what are considered compact algebras. So these are going to be over the real numbers. So you have SUN, SON, SP2N. So you should be careful. Hall uses indexes this just with N, but it really should, SP only exists for like 2N by 2N matrices. And UN, for example. So these are all over the real numbers. These are all really algebras, and these are sort of the basic list of compact ones. And so then Hall offers us this definition. There's various equivalent definitions, but he says that a complex Lie algebra G is reductive if G is isomorphic to the complexification of some compact Lie algebra. Roughly speaking, the reason why we care about reductive Lie algebras, and this term extends to Lie groups as well, is basically just because that's where the representation theory is the nicest. We can, in some sense, recover the group or algebra from its category of representations. So that's a brief explanation of why this term even matters in the first place. And he also gives us another equivalent definition. So we've already seen various equivalent definitions of semi-simple. One of them being that the representation theory works out nicely, that everything, all the irreducible, all the finite dimensional representations are direct sums of irreducibles. So it's semi-simple for a complex Lie algebra means that it's reductive and that the center is trivial. And finally, one other term that we're going to need is the compact real form. So the compact real form of a semi-simple complex Lie algebra G, this is a real subalgebra. Let's call it K, which is compact and G is isomorphic to K direct sum Ki. So of course, what I mean by this is you can think of this gadget here as, well, taking our complexification definition, or you can think of it as sort of formal linear combinations of x plus iy, where x and y belong to K. And so this is important. I'll maybe just say a quick word about real forms in general, where this idea comes from is that if you have, oh, I didn't prepare an example, so maybe I shouldn't say. So I think the example comes from the group SU2 and versus the equation, the algebraic equation x squared plus y squared equals 1. So if you look at both of these things over the complex numbers, it turns out that as geometric objects, as algebraic varieties, so not important that you know what that means, it's a set of polynomial equations, turns out that these two things are isomorphic. But if you do this sort of forgetting, right, and you just think about the solutions of these equations over the real numbers, they no longer are. So this is where the idea of forms comes from, is you have, say, two algebraic structures where they don't appear to be the same over some, if you look at them over some field F, they don't appear to be the same. But if you sort of extend your field of definition to look at these structures over the algebraic closure, then suddenly they become isomorphic. So in that case, we say that these two things are forms. And so when we're studying the idea of complex Lie algebras, there may actually be, because there's this question, we talked about taking a real Lie algebra and producing its complexification. And I mentioned before that this isn't really a bijective process, right? So you might wonder, well, what if I have two Lie algebras and when I complexify them, I get the same thing. What relationships do those have with each other? And by going down to either one of these real versions or real forms, what could we possibly learn, or what different information do these real forms capture? So that's where this idea comes from. So very last topic in this starting to get lengthy video is the notion of a Cartan subalgebra. So the importance of this is, remember, we talked about this general strategy in the representation theory of Lie algebras. And again, we're going to focus more specifically on just the general structure, but some of this representation theory comes into play there. Is that, basically we sort of, the goal is to find some sort of commuting, some abelian subalgebra, right? And we know from like linear algebra that we can simultaneously diagonalize operators that commute with each other. So we basically want to find the largest commuting subalgebra that we can, so it covers as much of the Lie algebra as possible, and take whatever representation we have, break it into eigenspaces for this subalgebra, and then look at what the remaining pieces of our Lie algebra do. So in particular, a Cartan subalgebra will be an algebra that is abelian. For all x in the larger algebra and h in h, if h and x, if the bracket is 0, then X is in H. So basically, we're saying this is sort of the maximality condition, right? Anything that X, trivially on the whole algebra is going to belong to this H. And also for all H in H, the adjoint action of H. So remember, this will be an operator from G to G, is diagonalizable. And so you've already seen examples of this, right? In SL2, it's basically just the span of this one element. And you can also, in SLN, more generally, it's just those diagonal elements that belong to SLN, the span of all of those. And so we have a couple, finish off with a final theorem about the structure theory, is that in general, if you have a Cartan subalgebra, then it will be of the form, it will be isomorphic to K direct sum Ki, where your so K is rather, sorry, it'll be of the following form. So H is a Cartan subalgebra in G. G is reductive, meaning that it's isomorphic to the complexification of some compact subalgebra. That compact subalgebra, if you take a maximal abelian subalgebra T, so just find the biggest abelian subalgebra you can, then H will be isomorphic to this. So there's two statements here. It says that every Cartan subalgebra is of this form, and given any maximal abelian subalgebra in K, so K is real, by the way, then if you take this direct sum, the thing that you get will be a Cartan subalgebra. And sort of the big result in the structure theory, both for representation theory, but also moving towards the classification of complex semi-simple Lie algebras, is that all of our Lie algebras are going to be isomorphic to, we'll always be able to find a Cartan, and we'll be able to find some direct sum or some other subspaces, so that we have a direct sum here. So this will be a finite direct sum. Of course, our Lie algebras in consideration are finite dimensional. And these spaces, these are eigenspaces for the Cartan subalgebra, and they're all one-dimensional. Right? So a good exercise, again, which we've already sort of done, is like, look at this for SLN, SLNC. So try and find, try and find, like, look at K from the list that we had above as a real subalgebra, consider its complexification, show that it's SLNC, so little lowercase, and see if you can figure out what the Cartan is and the one-dimensional eigenspaces. So start with SL2, start with SL3, then find the general pattern. Okay, that is it for this video, and I'll see you in the next one. Most